Hello, my wonderful chemists. I hope you're doing well today. We have two topics to talk about, polyatomic ions and their lowest dot structures, and then the second topic is resonance. So let's start with polyatomic ions, or really ions in general. So if you remember, we have been drawing lowest dot structures for monoatomic ions, something like O2 minus. So what we do is we look at the neutral atom first, like oxygen in this case, and we look at the valence electrons. So oxygen has 6 valence electrons normally, and so we draw that. So there's oxygen with 1, 2, 3, 4, 5, 6 valence electrons. That 2 minus is telling us that it has gained 2 extra electrons. So we add the 2 extra electrons, and then to show that it's an ion, we put brackets around it and then the charge. So we have done these at the beginning of the chapter. New is polyatomic ions. So if you recall, polyatomic ions are many atoms bonded together with an overall charge. So for example, NH4 plus is ammonium. So that means we have a nitrogen bonded to 4 hydrogens, and then all 5 of the atoms collectively have lost 1 electron here, and therefore the positive charge. So how do we draw these? There's different ways to draw them. So you can just kind of use your valence electrons like we've been doing. So I'm going to show you both ways. So the first way is to draw it normally. So nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. And then we're going to bond it to 4 hydrogens. Each of them has 1 valence electron. And we're going to also take into account that positive charge, which means that you have lost an electron. Now you can take it out of anywhere, because remember, when you're bonding, you can move those electrons around. So I'm going to choose to remove it from the nitrogen right here. So I'm going to erase it. My eraser's not working. There we go. And then I'm going to connect everything once. And then I check that everything has an octet. So nitrogen has its octet, each hydrogen has its duet, so everybody's good. So I'm going to just rewrite it so it looks neater, like this. And then because it's an ion, you got to put the brackets around and the charge. So that's what it looks like. If this was a negative charge instead of a positive charge, that means it has extra electrons. So you would add the extra electrons. And again, you can put it anywhere as long as you know that you can erase them and move on. So when it's positive, you take away the electrons. When you have a negative charge, you put in extra electrons. The other method to do it is to use the math that we had at the beginning of the chapter. So let me show you where that is. If you go up to page 6 of our packet, the second half of the page gives you some tips for how to draw lowest dot structures, and tip number 2 is using the math to figure it out. So let's review it real quick. So what you do is you calculate the number of valence electrons needed to make each electron stable. That means each element stable. That means 2 for elements before boron and 8 for everything else. Then you calculate the number of valence electrons available for your atom. You subtract A minus B, that gives you the number of electrons shared. Divide by 2, that gives you the number of bonds in the molecule. You draw your atoms, you link everything together, draw the correct number of bonds as indicated in part D, and then give everybody lone pairs so that all of them have a duet or an octet, and then double check that you've drawn the correct available electrons, which are in B. That's a lot of stuff, so let's actually practice it. So let's try it with PO4 3 minus. So let's start with the math. So first you want to decide how many valence electrons each of your atoms would like to have, would be stable with. And so basically hydrogen would have a duet, everything else would have an octet. So we have a phosphorus, one phosphorus that would like to have 8. We have 4 oxygens, each of them would be stable with 8 as well. So 5 times 8, that would be 40 electrons needed for everybody to be stable. Part B, you add up how many electrons are actually available to you. So for phosphorus, it has 5 valence electrons. We have 4 oxygens, each have 6 valence electrons. And then don't forget your charge. So that 3 minus tells us that there are 3 more electrons available. So we're going to add 3 more electrons to our available number of electrons. If this was a positive charge, like with ammonium, you'd subtract what it says there. So when we add these together, let's see, 24 plus 5, 29, 29, and 3 is 32. So 32 electrons are actually available. So we need 40 electrons, but we only have 32 available. So that means the difference between them, the 8 electrons, are going to be shared. Each bond takes 2 electrons. So if you take the number of shared electrons, divide that by 2, you're going to get that you get 4 bonds. So then what do? Then we draw our skeleton. So we have our phosphorus, and then we have 4 oxygens. Connect everything once, and check that you've drawn the correct number of bonds. We've drawn 4 bonds, and our math tells us that we should have 4 bonds, so we're done with all the bonds that we need. Next, you give lone pairs to any atoms that need it to get to the octet. So our phosphorus right now has 8, so it's good. Each of these oxygens right now only has 2, so that means each oxygen needs 6 electrons or 3 lone pairs. So put all your lone pairs. It is a polyatomic ion. If it has a charge, you put brackets around it, and then the charge. And then very important, you also count how many electrons you've drawn total. Make sure that it is equal to B, which is your available electrons. So I'm going to count them by pairs. So I have 1 pair, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs. That totals to 32 electrons available. So that is correct. Again, you could have just drawn it by putting in the available electrons, so doing your valence electrons for each of the atoms and adding 3 extra electrons just anywhere, knowing that you can move them around and connect everything to try to get octets. Okay, let's try the math one more time for cyanide ion, Cn-. So for part A, we're going to count how many electrons are needed for them to be stable. So carbon would need 8, nitrogen would also need 8 for a total of 16 electrons needed. That's 16 there. Next, we're going to count how many electrons are actually available. So carbon has 4 valence electrons, nitrogen has 5 valence electrons. Don't forget that negative here, which means that you have 1 more electron available for a total of 10 electrons available. You subtract the 2, that gives you the number of electrons that are shared. So we have 6 electrons shared. Divide that by 2 to give you the number of bonds. So it looks like we have 3 bonds. So then you draw your carbon, you draw your nitrogen, connect them once. And right now we've drawn only 1 bond. Our math tells us that we should have 3 bonds. So you need 2 extra bonds. There's nowhere else to put them except right here. There's only 1 spot. So that means this is a triple bond. Then you give lone pairs to the atoms that need it to get to the octet. So carbon right now has 6 electrons, so we're going to add 1 lone pair. Nitrogen, same thing, it has 6 electrons, so we're going to add 1 lone pair. Because it's an ion, we're going to put brackets around it and the charge. And very important, we're going to count how many electrons we have drawn total, and that should equal to the total electrons available. So I'm going to count in pairs again. There's 1, 2, 3, 4, 5. So 5 pairs means 10 electrons available, so that is the correct structure for it. So that's how you draw polyatomic ions. Either by just drawing it like we normally do or by doing the math. I recommend, if in doubt, when it's a polyatomic ion, use the math. Let's talk about resonance structures next. So let's define what resonance structures are, and then we're going to look at an example and kind of talk about what it means. So resonance structures are different but equivalent structures for the same molecule. The real molecule exists as the average of all the resonance structures. And this is not really going to make any sense until we actually do an example. So let's try an example together. So let's try TeO2 and see what it looks like. And for this year, I'm actually going to tell you how many resonance structures there are. So you'll see next to each of these examples, I'm giving you how many resonance structures. If you were to take AP Chem or chemistry in college at the next level, you are going to be expected to know how many resonance structures just by looking at the molecule. So TeO2, I'm going to go ahead and do my math for this one. So tellurium has 6, we're going to do how many electrons are needed first to make it stable. So tellurium would like to have 8. Then we have 2 oxygens, each would need 8 to be stable, so 3 times 8 is 24 electrons needed. Next, I'm going to calculate how many electrons are actually available. Tellurium has 6. I have 2 oxygens, each have 6, for a total of 18 electrons available. Subtract the 2, that's going to give you 6 electrons shared, which means you have 3 bonds. Whenever we have resonance for this year, we're going to, it's pretty safe to use the math. I would recommend that you do the math. It's always going to work. So we're going to draw these. So I'm going to start with the tellurium. And I have 2 oxygens around. So I'm going to put 1 here, 1 there. And since it's telling me that I have 2 resonance structures, I'm going to draw 2 of these. So another tellurium with 2 oxygens here. Now you want to connect everything once. So there's a bond, here's another bond, here's a bond, here's another bond. So we're drawing the same thing twice because we have 2 resonance structures. Now, when we've connected everything, we have drawn 2 bonds. However, our math is telling us that we need 3 bonds. So we need 1 more bond. Well, you have 2 choices, 2 spots where you can put that extra bond. You can put it right here, or you can put it right here. Okay, so we've drawn our 3 bonds. Now we're going to give lone pairs so that everybody gets an octet. So let's see, the double bonded oxygen right now has 4 electrons, so it needs 2 lone pairs. The tellurium has 6 electrons right now, so it just needs 1 lone pair. And the other oxygen that's singly bonded, it has 2 electrons right now, so it needs 3 lone pairs. I'm going to do the same thing on the other side. So this oxygen needs 3 lone pairs. This tellurium needs 1 lone pair, and this oxygen needs 2 lone pairs. Okay, let's check that we've drawn them correctly. You check by counting how many electrons you've drawn and checking that they're equal to the electrons available. So once again, I'm going to count by pairs, and if I want 18 total electrons, that means I need 9 pairs. So let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9. This structure is good. Let's check the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9. The structure is good. So those are two resonance structures. Between resonance structures, we draw a double-headed arrow. Now, the idea of resonance, if you've ever, heard of a resonance fork, how it goes back and forth. So the idea is that in reality, it's not that the molecule goes back and forth between those two structures. It's actually an average of those two structures. So in reality, it's not that this is a double bond and this is a single bond. It is actually a bond and a half to each of those oxygens. So this is a bond and a half, and this is a bond and a half. So those extra electrons that are in the double bond are actually moving around or resonating between here and here. So in reality, like I said, it's a bond and a half here and a bond and a half here. So resonance structures, like we said, are different. These two structures are different, but they're equivalent for the same molecule. And in reality, the molecule exists as the average between the two. So in reality, the tellurium is bonded a bond and a half to each of the oxygens. Let's try one more. So we're going to do the carbonate polyatomic ion. So let's do the math. We have a carbon that would be stable with 8. And then we have 3 oxygens that would be stable also with 8. So 4 times 8 is 32 electrons needed. Next, we're going to count how many electrons are available. So carbon has 4. 3 oxygens each have 6. And then that -2 means we have 2 extra electrons. So we're going to add that to our electrons that are available. So let's see, 3 times 6 is 18, plus 2 is 20, plus 4 is 24. So 24 electrons available. Subtract the 2, that's going to give you 8 electrons that are being shared. And you divide that by 2 to get 4 bonds. So we are told that we have 3 resonance structures. So we're going to draw a carbon, and we have 3 oxygens around it. Let's connect everything once. And we have 3 resonance structures, so we're going to draw this 3 times. Okay. The basic skeleton that we've drawn where we connect everything once, we have drawn only 3 bonds. According to our math, we have 4 bonds. So we have 1 extra bond, so we need to show where that extra bond is. Well, we have 3 options. We can put the double bond here, we can put the double bond here, we can put the double bond here. So with resonance structures, you'll see that usually you have single bonds and then 1 double bond, and that 1 double bond kind of moves around in different spots. So we've drawn our 4 bonds. Next, we give lone pairs so that we have octets. So our carbon is already good with 8 electrons because it has 4 bonds around it. So it has its octet. The oxygens need some more lone pairs though. So the double bonded oxygens have 4 electrons right now, so they need 2 lone pairs. So this one needs 2 lone pairs, and this one as well. And then our single bonded oxygens, they only have 2 electrons right now, so they need 6 more, so 3 lone pairs on each of those. And it's a lot of electrons, a lot of little dots. You do have to make sure that you are drawing your lone pairs, otherwise your structure would not be correct. All right, next we make sure we put brackets around it because these are ions. So brackets in the charge. And in between resonance structures, we put double-headed arrows like that. The previous one, we did not need the brackets because it was neutral. It was just a molecule. It didn't have a charge, but this one definitely we do need those brackets. And then finally, you want to double check. So you want to make sure that you've drawn the electrons available. So you want to make sure we have 24 electrons. So I'll count in pairs. If we need 24 electrons, that means we need 12 pairs on each of these structures. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That one's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the last one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are all good.